What makes an acid an acid? Is it that sour lemon tang? Or something much smaller, moving in a flash between molecules? In chemistry, the Bronsted-Lowry idea boils it down to a single tiny traveler, the proton. I'll show you how acids and bases are really just proton donors and proton acceptors. I'll show you how they form conjugate pairs. I'll show you how this explains strength, water chemistry, and more. Let's zoom in. According to Bronsted-Lowry, an acid is any species that donates a proton, H+. A base is any species that accepts a proton, simple as that. No need to be in water, no need for sour taste, just a proton transfer from one partner to another. When the acid donates H+, it becomes its conjugate base. When the base gains H+, it becomes its conjugate acid. So every acid-base reaction creates a matched pair on each side. Acid with its conjugate base, base with its conjugate acid. Picture hydrochloric acid meeting water. HCl donates a proton to H2O. HCl, H++, qual is the idea. But the proton doesn't float around naked. It's grabbed by water to make hydronium, H3O+. So the real transfer is HCl plus H2O, H3O+, plus Cl. Here, HCl is the acid, water is the base. After the transfer, Cl is the conjugate base, and H3O+ is the conjugate acid. Notice the symmetry. Acid conjugate base, base conjugate acid. Now flip it with ammonia, NH3 plus H2O, aka NH4 plus OHE. Ammonia accepts a proton from water, so ammonia is the base and water acts as the acid. Ammonium, NH4+, is the conjugate acid. Hydroxide, OHE, is the conjugate base. Here's the key insight. Strong acids have weak conjugate bases. HCl donates its proton almost completely, so Cl barely wants it back. Weak acids like acetic acid CH3COOH only partly donate, so their conjugate bases, acetate CH3COO, are relatively stronger at accepting protons. The same logic flips for bases. A strong base like OH makes a weak conjugate acid, H2O. Strength is a tug-of-war over the proton. If the forward donation is easy, the reverse grab is hard, and vice versa. Some substances can both donate and accept protons. They're amphiprotic. Water is the classic example. With HCl, water accepts a proton and acts as a base. With NH3, water donates a proton and acts as an acid. Hydrogen carbonate, HCO3, is another amphiprotic species. It can become H2CO3 by accepting H+, or it can become CO3 by donating H+. This duality explains why pure water self-ionizes ever so slightly. 2H2O, H3O+, plus OH. One water acts as acid, the other as base, producing equal amounts of hydronium and hydroxide at 25 degrees. That balance defines neutral pH. How do I spot acids and bases fast? If a molecule has a readily donatable proton on a highly polar bond, think HX, where X is very electronegative, it's likely an acid. If a molecule has a lone pair sitting on an electronegative atom like NO or a halide, it can accept a proton and act as a base. Remember, context matters. The same molecule can switch roles depending on its partner. H3O+, JICE, H2O, NH4+, NH3, CH3COOH, CH3COO. Quick mental model, follow the proton. Whichever side donates is the acid side, whichever side receives is the base side. Label their partners as conjugates, and you've mapped the whole reaction. Bronsted-Lowry reframes acids and bases as proton donors and acceptors. Every reaction is a proton handoff creating conjugate pairs. Strong and weak are two ends of a tug-of-war. The stronger the donor, the weaker its conjugate acceptor. Water sits in the middle, often playing both roles. Learn to spot the lone pairs, the acidic protons, and you can predict the flow. Hook, explain, recap, and if in doubt, track the tiny traveler, find the proton's path, and the chemistry falls into place.